this section, you will learn what is operational amplifier. You will learn on the basic theory of op-amp such as circuit structures, advantages, and applications of it.
Hi, in this section, you will learn on operational amplifier. First, let's talk about amplification. Amplification is an essential function in most analog and many digital circuits. We amplify an analog or digital signal because it may be too small to drive a load, overcome the noise of a subsequent stage, or provide logical levels to a digital circuit. Amplification also plays a critical role in feedback systems. It is also important for you to know performance of amplifier. The first one, what aspects of the performance of an amplifier are important? In addition to gain and speed, such parameters as power dissipation, supply voltage, linearity, noise, and etc. Furthermore, the input and output impedance determine how the circuit interacts with the preceding and subsequent stages. In practice, most of these parameters trade with each other, making the design a multidimensional optimization problem. As in figure here, such trade-offs present many challenges in the design of high-performance amplifiers, requiring intuition and experience to arrive at an acceptable compromise. In this figure, you will see the trade-off between noise, linearity, gain, power dissipation, supply voltage, input and output impedance, and also speed. All of these are depending on the requirement, the design specifications, the applications that you are designed for. Now let's see the circuit structure of an operational amplifier or op-amp. A MOSFET op-amp typically consists of a differential input stage, a gain stage, and an output stage, all built using MOSFET transistors. The differential input stage uses a pair of MOSFET transistors to compare the input signals and amplify the difference. The gain stage further amplifies the signal, and the output stage provides the final amplified output. There are a few advantages of MOSFET op amps. Here we list four of them. The first one, high input impedance. The MOSFET op amps have a very high input impedance, typically in the range of millions or billions of ohms, due to the high impedance gate terminal of the MOSFET. Second one is low noise. It generally have lower input referred noise compared to BJT op amps, making them suitable for applications requiring low noise amplification. The third one is wide bandwidth. It can operate at higher frequencies and have a wider bandwidth compared to BJT op amps. The last one is low power consumptions. It is typically have lower power consumption, making them suitable for battery powered or low power applications. Now let's have a look at the differences between operational amplifier and OTA. Let's take a look at the characteristic of OTA. First, it has high input impedance and also output impedance. It is suitable to drive high impedance loads such as caps or common drains or common source as next stages. It also modulates an input modulating voltage to output modulated current. Now let's have a look at the characteristic of op-amp. It has high input impedance similar to OTA. However, it has low output impedance. It can drive resistive loads as long as these loads are higher than the output impedance of the op-amp. In terms of modulation, it has input modulating voltage to output modulated voltage. As compared to OTA, it has output modulated current. The figure on this page provides a visual representations of the components that make up an operational amplifier circuit. The symbol on the left represents a generic operational amplifier. It has two input terminals, positive and negative inputs, and one output terminal. The circuit diagram on the right illustrates the internal structure of an op-amp, which includes an operational transconductance amplifier (OTA) and a buffer stage with a common drain source follower configuration. This configuration allows the op-amp to have a high input impedance and a low output impedance, making it suitable for a variety of applications. Now let's take a look at 5T OTA. 5T stands for 5 transistor. For a single stage OTA, a combination of PMOS and NMOS with a total of 5 transistors construct an OTA. This circuit used to provide a current gain from an input voltage. For DC operating point, the architecture is fully balanced. Once an AC swing occurs, a current is delivered to the load. The output DC operating point is set by the amount of the current flowing into the load. The circuit diagram here includes several arrows that depict the direction of current flow. The input voltage Vin is shown to be ranging between 500 millivolt to negative 500 millivolt. At the 200 millivolt input applied, the current output is 48% of the total 148% of input current supplied by the voltage supply. In other words, 148% of input current supplied will have a 48% of output current. The arrow pointing to the left shows that 74% of the input current is flowing through both T3 and T4 transistor equally at 74% each. However, as the current flow from T4 further down to T2, it branched out by 26% to T2 and 48% to the output. At T1, total current from T3 remained at 74% as no branch going down to the tail current. At tail current, 100% of the 148% supplied current here. So this 100% is contributed by the current flow from T2 and T1, which 26% and 74% each. Here is the important equations to indicate the performance of the amplifier. The first equation given by AV equals to GM1 times R out. This equation represents the voltage gain of the amplifier, where GM1 is the transconductance of one of the transistor and R out is the output resistance. The second formula is R out equals to RDS1 parallel with RDS2. This equation defines the output resistance as the parallel combination of the drain source resistance of two transistors. The third one is the bandwidth. BW equals to 1 over 2 pi times R out times C1. This equation represents the bandwidth of the amplifier, which is inversely proportional to the product of the output resistance and the coupling capacitor. The last one is the gain bandwidth. GBW equals to GM1 over 2 pi times C1. So this equation defines the gain bandwidth product, which is a measure of the amplifier's high frequency performance. DC biasing is generated by biasing the gate of the differential pair using any of the techniques described in a single-ended common source amplifier. The input common mode has a specific range that should be maintained to ensure proper DC biasing for the tail current source. The input common mode range is a function of a differential pair size, the tail current value, and the RD value, which is the resistance connected to the output. The minimum common mode is defined as VD saturation at current source plus VD saturation at N1 plus voltage threshold at M1. This represents the minimum input voltage required to keep the transistor in the saturation region. The maximum common mode is defined as VDD minus ISS times RD over 2 plus the voltage threshold of M1. This represents the maximum input voltage that the circuit can handle without the transistor entering the triode region. The circuit diagram shows a basic differential pair amplifier with two inputs voltage V in 1 and V in 2 and two output voltage V out 1 and V out 2. The tail current source ISS and the load resistors represent as RD1 and RD2 are also shown here. In this page, we will discuss the key characteristics of an operational amplifier circuit, specifically focusing on the following aspects: common mode gain, common mode rejection ratio CMRR, power supply rejection ratio PSRR. The first one is common mode gain. Ideally, the common mode gain of an op-amp should be zero, but due to mismatches in transistors and finite resistance of the tail current, it has a finite value. The equations provided shows the formula for calculating the common mode gain, which is inversely proportional to the conductance of the transistors and the resistance of the tail current. Second one is CMRR. CMRR is the ratio between the differential gain and the common mode gain of an op-amp. The equation for CMRR demonstrates that it depends on the transconductance of the transistors and resistance in the circuit. A higher CMRR is desirable as it indicates the op-amp's ability to reject common mode signal and amplify only the differential signals. So the last one is the power supply rejection ratio, PSRR. PSRR is a measure of the op-amp's ability to reject variations in the power supply voltage. The equation shows that PSRR is proportional to the transconductance of the transistors and inversely proportional to the sum of the transconductance of the other transistor in the circuit. So a high PSRR is desirable as it indicates the op-amp's insensitivity to power supply fluctuations. So these characteristics are fundamental to understanding the performance and limitations of op-amp circuits, which are widely used in analog signal processing amplifications and various other applications. Analyzing these parameters helps in design and optimizations of op-amp-based circuit to ensure their stability, accuracy, and robustness. In this last page of this section, provide some schematic design considerations for a current mirror array, which is a common circuit building block in analog electronics. So let's go through the key points. The first one is transistor matching. Second one is common wave. The third one is current scaling. All the transistors in the current mirror array need to have the same channel length to ensure proper current mirroring. So the second one, the common wave, the wave W should be common for all unit transistor in the array. The W value is determined by the number of fingers. W equals to W times number of fingers. So current scaling, multiple of currents can be obtained by using multiplier in the transistor. This allows the current to be scaled up or down as needed depending on the circuit's requirement. So there are times you will use the number of fingers. There are times you will use the multiplier depending on what you are trying to achieve. The schematic diagram here shows implementations of the current mirror array where M1 times W over L and M2 times W over L represent the sizing of the transistor in the current mirror. M1 ref and M2 ref are the reference transistor that set the mirrored current. So this type of current mirror is commonly used in analog circuits such as operational amplifier, where precise current matching and scaling are essential for proper circuit operation and performance. The design considerations highlighted in the image ensure that the current mirror array can accurately replicate and distribute the input current to the desired output nodes, which is a critical aspect of many analog circuits design. So that's it for this section. I'm gonna see you in the next section. See ya.